All right, so yesterday's lesson, we were introduced to kind of a theory that's on top of the valence bond theory, right? Remember, the valence bond theory simply states that when bonds are formed, we believe that there's overlap of the orbitals, creating what we would call a bonding orbital, and that, increases the probability of finding the electrons in between the nuclei, which then forms the bond. And then we encountered the example of CH4, and when we actually look at CH4 as chemists through various methods, we find that it cannot be explained using s and p orbitals. So this idea of hybrid orbitals being formed during the bonding process, again, works very well in explaining what we see, all right? So we have this idea of hybrid orbitals, and the first type of hybridization I introduced you to was sp3 hybridization, and that's when we have the s orbital along with the 3 p orbitals put together, kind of mashed up in a calculation, and then separated out into 4 individual sp3 orbitals, which are identical to each other. And when their shape is determined mathematically, we find that the 4 orbitals point off in opposite directions to each other, resulting in this tetrahedral shape, all right? And so when we have sp3 hybrid orbitals, they result in a tetrahedron, and we can explain all kinds of things with that. The electron pair arrangement is the term I like to use to describe the shape in which those electron pairs will be oriented, and the types of pairs that we can have, just as a reminder, are bonding pairs, which would be one of those sigma bonds, or lone pairs, which is just a lone pair of electrons. So what if it turns out that we don't need 4 identical orbitals for bonding, but we only need 3 identical orbitals for bonding? And if that's the case, and I'm struggling to advance my slide, here we go. If that's the case, then, oops, back up. I didn't want to go too ahead. Going back, everything's working very slow here today. Then we have something called sp hybridization, all right? Now, in sp hybridization, we still have our s orbitals and our 3 p orbitals, but we only use 2 of the p orbitals. So you can see here the hybridization results in 3 orbitals being identical to each other, and then because the last p orbital was not used, it still exists as an unhybridized p orbital. All right, now in a moment, I'm going to draw an image of the orbital. I'm going to draw it down here, and that's the one that I'm going to want you to draw. All right, and so if only 3 orbitals are needed, it turns out that we have this sp2 hybridization. Notice in sp2 hybridization, an s and a p means that 3 identical orbitals are formed, and therefore you can see 1, 2, 3 sp2 orbitals, but a p orbital is not hybridized and still exists, and we need to indicate that. Now, when that bonding takes place, again, another little odd thing happens. When we fill our electrons in those sp2 orbitals, if there's 4 electrons, there is a little bit of a promotion, because that p orbital is of slightly higher energy, but it is promoted, and again, we have kind of Hund's rule that's stating we're going to half fill all of those electrons. Now, with 3 identical orbitals, we get a change in shape. If I have my tetrahedron here, all right, and we remove this orbital, I'm now down to 3. Due to electron repulsion, these 3 will try to spread out from each other. They'll push each other out, and will result in this flat shape that is triangular shape. So the three orbitals will result in a triangular planar shape. And so the EPA, oops, back up, I thought it was going to come up. The EPA is triangular planar. Triangular meaning it's a triangular shape, and planar meaning it's flat. Now let me draw this for you. I'm going to draw the triangular planar shape as if it's kind of coming in and out of the board. Yes. I have no idea. This is 22 by the looks of it. I'm continuing. So now at this point, I'm going to draw that triangular planar as if it's coming out of the board. So I'm going to have one of the triangular planar right there, flat in the plane. The second one I'm going to draw as if it's coming out of the board at us. So out of the board, kind of on an angle. The third triangular planar I'm going to put in behind. So it's going to look a little smaller. It's going to be in behind. So there it is in behind. All right. I'm going to draw a black line here and a black line there through the mid of those orbitals. And I'm going to indicate here that this is 120 degrees. Okay? Now, on my picture here, I've only got 3 of the orbitals labeled. 1, 2, 3. There's the 3 orbitals. There's actually a 4th orbital still there that I haven't drawn. And that 4th orbital is the p orbital that isn't hybridized. It looks like a regular p orbital. It's got 2 lobes. The orientation of the p orbital is up and down. It's perpendicular to this plane. So using the black, and hopefully this doesn't get too complicated, it goes up and it goes down. So there's the p orbital. There's the 4th orbital there. All right? So sp2 has 3 identical orbitals which push out into the opposite corners of a triangle, an equilateral triangle. That makes the angle of the adjacent bonds 120 degrees. We call that shape triangular planar because it's triangular and it's flat. And the unhybridized p orbital sits up and down from that plane. This may look as if there's 5 orbitals here because of the 2 lobes of the p orbital, but it's only 4 because that p orbital always has 2 lobes to it. So only 2 electrons can go into that p orbital. So again, there's only 4 orbitals here. 1, 2, 3 sp2 hybridized orbitals, with 4 being an unhybridized p orbital. Okay? And that's what happens when we only need 3 pairs. All right? Let's take a look at the last type of hybridization that I'll be dealing with today. But tomorrow we will continue and learn a couple more types of hybridization when we talk about the expanded valence. So, let's say we're in a situation where we only need 2 orbitals that are identical to each other. Well, then we only need an S and we need a P, one of the P's. Put them together in the mathematical blender, pull out 2 identical orbitals, create what we call sp hybridization. And because we've only used 2 of those orbitals, there are still 2 unhybridized p orbitals. Now you can see up here in the graphic that when we have 2 orbitals, and it's not too difficult to imagine, if I now take my flat triangular planar and I pull one of those off, these 2 are going to repel away from each other, and they're going to repel to get as far apart from each other as possible, and I can't bend this to be the right shape, but it'll end up being linear. It'll be a nice linear molecule. So again, looking at the EPA, we will just call that linear. So it's a linear shape. And drawing the 4 orbitals, the 2 hybrid orbitals, there's one flat on the board. There's 2 going the opposite way. And that's really not a very good job because it should be the same shape, like the same size. But my eraser doesn't work, so I'm not going to go back. And again, I'm going to draw a line up the middle here so that I can represent the bond angle between those things. And that's going to be 180 degrees. And now I have 2 unhybridized p orbitals that should also be represented here. And the 2 unhybridized p orbitals, well, one of them, and again I'm going to use black. Actually, I'll use the yellow first. One goes up and down, just like we did on the last one. And this is going to make our picture a little more complicated. The second one comes out of the board. So that's that situation where it comes out front and then hides in behind. I tried to make it look as if it was hiding in behind there. This picture, you might think, looks like 3 p orbitals. One in the X, one in the Y, one in the Z. But it's quite different in that we've taken an s orbital and mixed it with a p orbital to create 2 separate orbitals. So looking at this picture, there are actually 4 distinct orbitals in here. 1, that guy can hold 2 electrons. 2, that guy can hold 2 electrons. 3, which is the p orbital, so 2 electrons can go in it, up and down. And 4, which is the other p orbital, 2 electrons can go in it. So again, in this particular shape, only 4 electrons can be stored. If I have 3 individual p orbitals, 1, 2, 3, and there's only 1, 2, 3 orbitals there, only 6 electrons can be stored. That's a different system. That's unhybridized p orbitals. The s would be in there. That would make 8. But when we hybridize it, we take an s and we take a p, that creates the 2 sp orbitals, and we still have unhybridized p orbitals that can do some other stuff. Okay? So normally what I do at this point is I'll get a piece of chart paper out and I'll draw all these things on the chart paper, and so that it can be out in front of us and it can help us think it through. I'm not going to do that right now during the video, but tomorrow, kind of as a review, I'll put that all on the chart paper and we'll use it to think it through. Okay, so we have our 3 types of hybridization. Let's now use this in order to now explain the bonding in some other structures. There is some representations of sp2 and sp, right? So in sp2, we take an s and 2 p's, put it in the blender, it spits out 3 orbitals that are triangular planar. And then again, we've got the unhybridized p orbital. In this case, it would be coming out of the board. It would be coming out and going back in because they've got theirs flat. Here we take an s and a p, we put it in the blender, we get 2 of them, and we get an s and a p heading in opposite directions. And then the unhybridized p orbitals are still perpendicular to those 2. Okay, so let's deal with some molecules here. And we're going to start with a couple of examples that we call electron deficient molecules. All right? So beryllium and boron. Well, boron is above the stair-step line. It is considered a nonmetal. It will undergo covalent bonding. Beryllium technically is just on the other side of the stair-step line because it's just back over here. And it also contains sometimes some nonmetallic properties. So even though beryllium is in the metals side of the world, it does have the ability to form some covalent bonds when it comes to bonding with the nonmetals. So we can draw Lewis diagrams representing covalent structures when it comes to beryllium as well, okay? Now, up to this point, when we've been drawing molecules, we've been telling you octet rule, make sure there's 8 electrons around all of the atoms so everything is happy. This is an exception to the octet rule. So now our exceptions to the octet rule are growing. Back in grade 11, we would have said, octet rule, make sure everything has 8 electrons around it. Oh, except for hydrogen. Hydrogen's a special case. It only needs 2. We now know it only needs 2 because it only has a 1s orbital, and it can't have any more than 2. Now we're saying, octet rule, make sure everything has 8 electrons around it, except for hydrogen. Oh yeah, and boron. Okay, and beryllium. Those are special cases as well. They can have stable structures without 8 electrons. That's why we call them electron deficient, all right? They can have stable structures with 8 electrons. They can bond in such a way, if there's enough electrons and if there's enough atoms around to share things, they can have a stable octet, but there are compounds in existence, they tend to be gaseous compounds, with boron and beryllium that do not satisfy the octet rule. So that's the examples we want to talk about today, the ones that do not. But they can also form bonds with 8 electrons around them. They can form enough. But there are examples that don't. So let's take a look at, and actually I'm making a change here. We don't want fluoride. We want beryllium hydride, BeH2. Now, to be honest, I'm not even sure whether BeH2 exists. I do know that BeF2 exists, but when I draw the energy level diagram, it's going to be painfully complicated to draw an energy level diagram with F, because you've got to draw all the S and P orbitals. We're going to draw it just as H to make it easier. So let's start with the Lewis. I should have actually, and I'm now a little annoyed, I should have actually opened up the notebook. The smart notebook's easier to write on, so hopefully I don't run out of space here. So let's draw the Lewis diagram for this. Well, beryllium, Be, has only 2 valence electrons. It's in group 2. Hydrogen has only 1 valence electron. So when this compound is formed, it's going to look like this. And that's all the electrons there are. There are no other electrons that are around, that are available to form any more bonds. So that's it. We have to stop. From grade 11 point of view, we would say, oh, that poor beryllium, it's so unhappy. But in actual fact, that's good. That's the stable structure. So let's now analyze it the way I've asked you to analyze it. How many bonding pairs are around this? Bond pairs. How many? For those who are sitting there silently, who don't like to share their answers, or for those of you who are sitting silently, oh no, what's the bond pair again? That's the bonds. That's the sigma bonds. So how many sigma bonds are around this thing? James? 2. 2 bond pairs. 2 bond pairs. How many lone pairs are around this? For those of you who can't remember what a lone pair is, those are the dots when they come in pairs. Okay. So how many lone pairs? Jocelyn's offended. How many lone pairs, Jocelyn? None. Correct. 0. 0 lone pairs. So in the end, we need only 2 pairs. We only need 2 bonding orbitals to fulfill this. If I only need 2 bonding orbitals, what type of hybridization is needed? I only need 2. We've got to squeeze together some orbitals, and we've got to start with S. So what would it be, Jocelyn? SP. And I stop there because I'm at 2. If I needed 3, I would have said SP2, right? Because I'd need 2 P's. So SP. So now, our little analysis of the bond pairs and lone pairs are going to tell us the hybridization. So if we know the hybridization, we now also know the EPA. How are these orbitals going to be shaped around the center? What did we call the shape? What's the EPA for SP? Look back to your notes now. Kira? Linear. They're going to be on opposite sides. Linear. Linear. Now for the energy level diagram. We've got beryllium. The E goes back to hydrogen. And all we have, well, actually, it's not that all we have, but we've been told that the hybridization has to be SP. So what I do is I draw 2 ovals because I've been told it has to be SP from the logic I just used. I also have 2 squares left. I have SP, and then those are the P. How many electrons do I have in the valence shell of beryllium? 2. There's only 2 in there. 1, 2. And now this is where we're really happy that I changed it to an H. Because if it was an F, I'd have to draw fluorine and put it back to helium and draw an S and draw some P's and have 1 in the last P and make a loop to share with that last P orbital, which could easily happen. But it's a real pain to draw. So let's just put in our H's like we did yesterday. There's my 1s of that hydrogen atom. Let's make a sigma bond out of it. And let's do a 1s electron again from the second hydrogen. And let's make a sigma bond out of it. So those are my hydrogens. Like I said, if it was a fluorine, I'd have an S that was full and a P that had 5 of them in it. There'd be 1 more left in the last box. I'd have to overlap that with that S, which can exist. It's a real pain to draw. Now let's do the orbital view. The orbital view. So, orbital view, I need 2 sp orbitals in opposite directions. 1, 2. Not bad. About the same size. That's fun. They each have 1 electron in it, so they're going to make a sigma bond, end-to-end overlap. Oh, I've made that pretty big. The hydrogen atoms are not that big, but that's okay. We get the idea. And those are the sigma bonds. We'll put a little sigma in there, little sigma in there. Those are my sigma bonds. They're oriented in opposite directions. The bond angle would be 180 degrees. 3D Lewis. All right, 3D Lewis isn't very exciting. Our 3D Lewis is actually the same as our actual Lewis that I drew because I put them on opposite sides. So for a 3D Lewis, all you got to do is put them on opposite sides. Like that. And we would say that the bond angle is 180 degrees. And that's what we see when we investigate. At least BEF2 is what we see. All right? So beryllium compounds can be happy if they only have 4 electrons around them. All right? Little exception to the octet rule. Let's take a look at a boron compound. And again, I used F, but I'm going to change that to an H. We don't want to draw all those F's. So let's deal with BH3. Let's just not worry about that guy. So again, we're going to go through the same logic that we've been doing. We're going to have a Lewis. We're going to have the energy level diagram. Once we figure out all of that stuff, we're going to do an orbital view. And then we're going to do 3D Lewis, 3D Lewis. Again, if you've got pencil, this is not a bad thing. This is something that you can do ahead. Now we're talking about boron. It has 3 dots around it. I'm going to put 3 hydrogens with that, and then I'm done. I'm out of electrons. So the boron has an H, and then a third H, and it doesn't have a lone pair because it's short 2 electrons. Right? The reason nitrogen has a lone pair is because it's 1, 2 over to the right from boron, and those 2 extra electrons make up the lone pair. This thing is 1, 2 short of nitrogen, which means its Lewis diagram simply doesn't have the lone pair because it doesn't have those 2 electrons that nitrogen has. So we're out of electrons. We must stop. Now for the analysis, I always point at that central atom because I want to make note. Bond pairs. Braden, how many bond pairs are there? 3. 3 sigma bond pairs. 3 bond pairs. 0 lone pairs. 3. Therefore, what type of hybridization is it? Braden, you got it? SPP, because I need 3 of them. That's where that 3 and the SP2 come together. That's the same thing. Therefore, it's SP2. SP2. Oops, I already wrote. Oh, no, I didn't. EPA. What would the EPA of this? How are those SP2 orbitals oriented with respect to each other? Braden, you got it? EPA, that's the shape. Trigonoplanar, triangular planar, however you want to say it. I'm going to just write down here trig plan. See how I did that? Trig plan, a little short form. You can do that on tests if you need to. Just write down trig plan. We know what that means. We means it's triangular planar. It's a triangular shape and it's flat. All right? Okay. Energy level diagram. Boron. Helium. You know what? Out of all of these things that we have to draw, even though the orbital view can be a little tricky, I hate drawing the energy level diagram. It seems like, wow, really? We're going to draw that again? As we get going, we're going to jump over the energy level diagram. We're going to forget about the energy level diagram. But right now, we're going to use the energy level diagram to get an idea on what type of bonds are formed. But soon, we will be able to just forget about it. So we're using it right now kind of as a way to help us think through the bonding. Since it's sp2, I need 3 ovals. And then I need a P that is unhybridized. This is sp2, and this is P. Notice I'm not putting numbers with it anymore. We can have other elements also behaving in this way that are lower down, so I'm not putting the numbers in. Valence electrons, 1, 2, 3. We don't have any more electrons, so we can't do anything with it. We're bonding hydrogens to it. 1s, that's overlapping like that. That's a sigma bond. 1s, we're going to overlap like that. That's a sigma bond. 1s, we're going to overlap like that. And there's our 3 sigma bonds with those sp2 hybrid orbitals. Because I don't need to represent the p orbital, the easiest way to do the orbital view is flat on the board. So remember in my last one, I drew it like this. Let's turn it by 90 degrees, and let's just put it flat on the board with these 3 orbitals pointing in 3 directions. So one out that way, one that way, one that way, to be 120 degrees from each other. And I'm going to overlap that with some hydrogen. Okay? And so 1, 2, 1, 2, 1, 2. I apologize for squeezing those electrons in that overlap space. And 3D Lewis, the only change we need to make on the 3D Lewis is I can't have these right angles anymore. I have to have a certain angle between them. And what should that angle be? What's the angle for sp2 hybridization? What do you got? 120. You can think of it like being 360 degrees, but I've got to divide it into thirds. So 360 divided by 3 is 120, right? That's how you get the angles in an equilateral triangle as well, right? Same type idea. So I've got to have one up here, and then I want to do my best to have one down there off that side and have one down there on that side, and that is indicating the trigonal planar shape, okay? All right, so at this point, I would normally be finished yesterday's lesson, all right? And now I'm assigning you worksheet number 2, which just has some other examples on it for you to draw and do some various things. But I'm going to continue on from here with the double and triple bonds, because it does extend right on from this. But I'm going to stop the recording because I've already got a good video of double and triple bonds, and it makes no sense for me to continue recording, and it's nicer to draw on the board. So I'm going to just stop recording here for a moment. If I can get that recorder up.